Until recently, deploying an AI agent meant watching it closely. You read every response, nudged it with the next prompt, and caught mistakes before they compounded. The agent did the reasoning, but the engineer held the guardrails by hand. That works for a prototype, but it does not scale. To build reliable systems, we have to remove the human from every single turn. This pathway follows a technical buildup. Prompting gave the model instructions, context gave it data, and harnesses gave us a way to test. Loop engineering now orchestrates these elements over time, allowing the system to run without manual supervision. Look at this basic flowchart of a while loop. In the Anthropic Claude team's precise definition, a loop is an agent repeating cycles of work until a specific stop condition is met. A loop agent returns to the start of the cycle, carrying updated information into the next iteration. Notice how each repeating cycle follows the exact same structure. The agent observes its environment, plans a course of action, and executes that action. Then comes the crucial breakout path, the verify step, which checks if the work meets the required standard before allowing the loop to exit. Without a clearly defined stop condition at that verification stage, your agent is stuck in an infinite cycle, burning through tokens and racking up server bills without oversight. But by enforcing a structured loop, that same agent becomes a reliable operational system. Not all tasks require the same architecture. The right type of loop depends entirely on two specific variables: what triggers the work to start and what constitutes the task being fully complete. This four-quadrant matrix maps out the primary enterprise loop types. Turn-based loops are triggered by a direct user chat prompt. Goal-based loops activate upon receiving a defined objective target. Time-based loops run on a scheduled clock interval. And proactive loops fire immediately in response to an external alert, like a webhook or a breached data threshold. To handle more complex tasks, LangChain's framework outlines how loops nest inside one another. Each level adds a new layer of quality guarantee, stacking capabilities as the computational demands of the task increase. This architectural model illustrates how we build that stack. The foundation is level 1, the standard agent cycle, where the LLM executes tasks. Directly on top is level 2, verification. Here, a second agent, or an automated test suite, reviews the output of the first layer, sending it back if it fails to pass inspection. Expanding vertically, we reach level 3, the event-driven loop, designed to process a continuous stream of incoming data lines. Finally, level 4 is the hill-climbing loop, branching out into multiple parallel execution paths to test, score, and refine different candidate solutions simultaneously. Every layer adds massive cost and complexity. As a practical rule, most of your daily business workflows only require levels 1 and 2. You should reserve the processing power of levels 3 and 4 exclusively for tasks operating at massive scale or with exceptionally high stakes. When an autonomous AI system breaks down in a production environment, the failure almost always traces back to one of 3 specific architectural flaws. The first flaw is context exhaustion. If an agent appends every single observation to its memory window, long-running loops will eventually drain the token budget. The fix is to compress completed steps into a single, dense block, a structured scratchpad, retaining only the raw details of the current active step. The second flaw is termination. Left to its own judgment, an agent might run infinitely. To prevent this, you must install a rigid barrier, a hard programmatic stop condition, and a maximum iteration limit that triggers entirely independent of the LLM's own decision-making process. Now, consider a level 1 agent that just drafted a highly complex financial report. Should you trust that exact same agent to accurately grade its own math? This diagram illustrates why the answer is no. If you ask an LLM to check its own work, it will often hallucinate false positives and confidently agree on a wrong answer. The fix is a completely separate deterministic checking layer, like a programmatic scanner running schema validation, that operates strictly outside the AI node. By implementing a structured scratchpad, enforcing hard stop conditions, and relying on deterministic validation, you transform a fragile, experimental loop into a robust architecture capable of operating in heavily regulated enterprise environments. In the enterprise, the constraints are tighter. If an agent's output affects financial transactions, healthcare data, or legal status, regulatory compliance is non-negotiable. You cannot rely on an LLM as judge for factual correctness. You must implement deterministic stop conditions, like confirming a database row successfully updated before moving on. This workflow pipeline shows how to maintain an airtight audit trail. Every single loop iteration deposits its context, actions, and results into a persistent storage vault for mandatory trace logging. If a loop reaches its maximum iteration limit without passing verification, the system triggers an alternate routing path, escalating the full trace directly to a human dashboard. When all these components align, you get a fully realized enterprise loop. The pipeline lights up sequentially, firing from a proactive external trigger, successfully passing through a rigorous deterministic verification node, and reaching a secure, verified termination. This typographic cheat sheet captures the entire system. Success in autonomous AI depends on loop engineering, building the enduring architecture that orchestrates the work. Master these 4 types, these 4 levels, and these 3 architectural fixes, and you can build autonomous systems that keep running long after the conversation ends.